Okay, so I'm going to talk about, I'm going to give a science motivator, hopefully motivating. And I'm going to talk about EarthScope some more. And well, I'm going to emphasize recent results and opportunities for geochronology. And I won't talk very much about geochronology that's been applied in EarthScope, but there has been. So I don't want you to take away that it's not happening. So that's really important. But I think that especially this group maybe isn't that familiar with some of the really exciting things that are coming from EarthScope research. And so I thought I would highlight some latest things, but also to talk kind of bigger scale kind of motivations. So first one is we're talking about the sort of structure and evolution of a continent in North America. And so just this really spectacular paper and sort of compilation of data by Steve Whitmire and Carl Karlstrom, kind of showing the sort of state of North America at about half a billion years ago, and you can see it's really all about time, and really talks about the kind of amalgamation that is sort of building the continent, but also the rifting that tears it apart. And so we need, the geophysical observations from EarthScope kind of give us opportunities to characterize the sort of structure of this and the material property distribution. And then the Plate Boundary Observatory gives us a chance to look at the sort of motions of these materials at the sort of decadal time scale. And then scientific drilling from SAFOD gives us kind of a really detailed view of a plate boundary fault. So then another way we can think of this is a model starting about when that last slide ended of kind of what this sort of geologic, sort of stratigraphically defined cartoon of kind of the evolution of North America. And this obviously has a huge amount of geochronology in it and some geological whimsy, but is kind of really spectacular. But it's a model of what has happened, and so obviously we need to test it. So here's another kind of a model, and it's more physics-based, but obviously quite idealized. It's kind of full mantle flow. The red is material that's coming up in plumes, and the blue would be the material that's going down. And this has cycles that are hundreds of millions a year time scale. But clearly there's an interaction between the lithosphere and the asthenosphere, and we need to examine that. And these kinds of models are really powerful for kind of building some intuition, but they have to have data to constrain them, right? So that's where we need geologic, geochronologic, and geophysical data. So I'm just going to, maybe you're hungry, I'm still a little bit hungry, and was thinking about some nice cheeses, but really I'm just going to give a short sampler of some EarthScope science for the next 20 minutes. So I'll start with kind of the seismological results, kind of the structural results. And so this is work from MIT group, kind of able to update sort of almost on an annual basis as the transportable array has moved across North America. Their models for the seismic wave speed underneath North America. And so this is the P-wave velocity model kind of perturbation, so plus or minus 1% of an average. And the main point is that we're able to kind of characterize relatively faster, which would be blue, and relatively slower red zones at much finer spatial scales than have been possible previously. Maybe it's a matter of relative fineness. It's sort of still at the kind of 100-kilometer length scale that it's refined, not at the 10-kilometer length scale. That would be one of our aspirations going forward. But you can see these slices going across where we have kind of a sort of combination of fairly slow and fast material in underneath Western North America. You can see pretty well imaged now the Farallon slab and that comes down underneath Cascadia is quite, I think, robustly imaged. That's gone by the time we get to where the San Andreas is, and we have the sort of wide zone of slow material underneath western North America, which I'll show in a couple minutes, probably provides extra buoyancy to keep the topography high. And then over here in the east, we have a pretty cold craton that's quite thick. And so this is North American craton. This is Farallon slab. So we can still, at least in an interpretive sense, track where this slab has gone, because we know we've had a significant amount of convergence between Pacific and North American plates for 100+ million years, as I showed in that cartoon. So we can track that material, we think. So here, then, moving a little bit more to a result that's a little bit finer scale, is what's the depth to the MoHO? What's the crustal thickness? And this has always been something that's hard to put your finger on, because it's difficult to measure without kind of an array. And the MoHO is this important transition in material properties, which is really manifest as a transition in seismic wave speed. And so that interface can be identified as a reflector or as a phase. You can get P to S conversions and look at sort of delay times. And so what we can see is we start to be able to get a map showing that, like where some of us live in Arizona, we have pretty thin crust, 28 kilometers. But once we get into the Rockies and beyond, we're talking about 50+ kilometer thick crust. Here's another view of kind of most of North American crustal thickness by a slightly different method, but we still see those sort of thin pieces of crust in the west with sort of more heterogeneous distribution of these blocks that have been ripped apart more recently or modified more recently, and then our pretty thick cratonic crust. So one thing that's been quite interesting, and there's been some nice work on this, and this has really valuable predictions for surface uplift, is the question of what does variable mantle flow or asthenospheric flow do to the topographic elevations. And so this map, just from a Becker et al. Paper, shows that once you account for isostatic variation, once we know crustal thickness and we think we have crustal density variations mapped out, and even if we try to figure out, well, where's the base of the lithosphere, we still can't account for as much as 1.5 to 2 kilometers of excessively high topography in western North America, and that probably is explained by added buoyancy from asthenospheric flow. So to me, this was quite exciting, because it starts to identify or indicate that there are these long wavelength surface displacements that come from interactions between the asthenosphere and the lithosphere that we might look for in sort of surface response and variable rock uplift or exhumation that we could examine with some of the tools that we're talking about in this course. The reds are zones of volcanic activity less than 20 million years ago, and blues would be older than 20 million. So there's excessively high topography in the base of the range, but you can see there's almost a dynamic pulling down of like where we are because of subduction. So it's sort of sucking the topography or the lithosphere down. And one thing about the Colorado Plateau is it doesn't seem to be having as much of an asthenospheric buoyancy explanation for its topography. So moving on, you can use these arrays to locate earthquakes, and one thing is we can tell the time of day by where the earthquakes are. So there's a lot of mining activity in North America, which is we have a $100 million seismic array that we can discover. But one of the interesting things is that there is a lot of earthquakes that are not just at the daytime, but are of quite great interest, like these in Oklahoma that are almost for sure induced by wastewater injection. Also, some are not as clear here in Pennsylvania and Ohio. And then, of course, there was this earthquake, which we don't necessarily think was induced, but is an important seismic hazard for eastern North America's reactivation of pre-existing interfaces, geologic interfaces. It seems that if you look at the seismicity, it tends to be localized along gradients in crustal structures. So these variations, and maybe in buoyancy or pre-existing zones of weakness, help localize the seismicity. Of course, we know the plate boundary, but everywhere else is more sort of distributed interplate deformation And it seems that much of that seismicity is on some of these crustal structural boundaries that we've been able to image with U.S. array with seismology. This map just is the gradient in one of the seismic wave speed maps. So another thing that people have been working on is Yellowstone, and it's kind of a lot of argument in literature about what's going on. And so 3 different slices through the upper mantle underneath Yellowstone seem to all pretty well show that there's this low velocity anomaly extending into the lower mantle. So is it a hot spot? We don't know, but there's definitely slow material pretty well defined there. One of the interesting things is it seems to be interacting in a kind of a complicated geometric way with the slab. And so important work going on there. So now let me transition a little bit to more kind of plate boundary observatory or deformation related results. And so this is a really thought-provoking summary diagram from Anke Friedrich paper, where it's basically time going to the left to the present and displacement that you might measure along a fault or with GPS. And so what they try to show is that different sort of external driving conditions kind of change the rates of deformations in fault systems. So at this sort of long time scale, we basically can think about reconfiguring fault zones or fault zone evolution with maybe different rates. And we might want to look at those kinds of questions with geochronology tools. Then at the kind of second order time scale, we might be able to see that there's important interaction between fault systems that kind of drives bursts in strain release, maybe earthquake clusters, and then those might be separated by times that are quite a bit more quiet. And we definitely want to sort of understand that time scale. Totally need geochronology tools for it. And then at the sort of finest time scale, kind of hundreds to thousands of years, is the individual earthquake cycle time scale. So what happens in the earthquake, and then this little blip here. I was confused at first because I thought time was going to the right. I was like, why is the post-seismic on the wrong side of the earthquake? The time goes to the left here. So this little blip is some kind of post-seismic acceleration of deformation. So these are deformation signals that we want to measure. We can use geodesy for them, but we can also use geology and geochronology. So just a quick thing that's of some relevance for us. So we're here in Vancouver. We're sitting basically on top of the Cascadia subduction zone. There's an important locked patch that's a little bit outboard of us, but we're sitting on the part that has this kind of episodic tremor and slip. It seems to slip quietly and slowly, but in ways that we can measure with geodesy. So this shows the displacement, and then these are sort of tremor, so seismic energy being released. And this is a new result here from Mark Simon's group that shows one of these events kind of propagating along the interface below the locked patch. So the locked patch would be here, and this shows slip, so it's millimeters a day, so it's not that much motion. But it also generates some seismic energy, which is the red dots. And so this is this sort of slow slip at the base of that big locked patch of Cascadia that we can see now. And so this is a really rich view of the behavior of faults. It's somewhere between aseismic and fully seismic. And so it has huge implications for how we think Cascadia or these big faults work. So then this I showed before. This to me is really the spectacular triumph of having 1,100 continuous GPS receivers measuring the deformation of Western North America over the decades. So it averages all that motion. And so it sort of corrects for any earthquakes that are in there. And the colors show the strain rate. And so we can see, I guess good for us who live in Arizona, we're not straining too bad, but it's nice to have a few earthquakes every now and then. But at least we can drive to California when there is a big earthquake. Here you can see the Wasatch Front is straining a little bit. Interestingly, Eastern Basin Range is pretty solid, doesn't seem to be deforming much at this time scale, but once we get into kind of the Walker Lane, we see this distributed deformation there. And of course, the San Andreas plate boundary has high strain. So this is quite valuable and really interesting, just seeing the deformation of North America. And so, of course, we want to push it back in time. And, actually, I have one more sort of decadal timescale geodesy result. So this is GPS, but also INSAR. So this just shows the sort of velocity gradient across the creeping part of the San Andreas Fault. So part of the San Andreas creeps, and we can really see that. So the color difference here just shows the difference in kind of line of sight velocity from a radar satellite. And this is also and so then if you map, you sort of take the San Andreas and lift it up and look at it from the side, these colors show the relative slip rate that we think is occurring along there. So the redder ones are faster. We think the San Andreas slips about 35 millimeters per year. And so parts of the creeping section look like they're going that fast. But parts don't. The blue ones means that they're sort of mixed creep, and they probably are building up stress that has to be released in maybe moderate earthquakes. And so the other thing we can think about is the transition on the ends of the creeping section to these fully locked zones. So this is Parkfield, is kind of a really interesting part of that transition zone, mixed behavior. And then this would be coming in San Francisco Bay Area. It's pretty abrupt there. So, but let's push this back in time. So there we need a little bit of Quaternary Geology and high-resolution topography. So this is a really pretty view of the San Andreas cutting through these really nice meanders here, and these terraces have these really nice offsets. So we need geochronology to figure out how old they are. We can see the marker with this LiDAR topography, but how old is that marker? So here's another, when we look at the high-resolution topography and we have repeat topography that bounds an earthquake, we can difference the topography and actually get direct 3D displacements between earthquakes. And so this was a paper that Mike Oskin took the lead on, and this was, we had Mexican Cartographic Agency topography from 2006. Then the 2010 El Mayor Cucupa earthquake occurred. We got new topographic data after, and we could basically subtract them and get a really rich view of the displacement field in the earthquake. So then drilling into the San Andreas. So the San Andreas, basically San Andreas Fault Observatory at depth, the idea was let's go down there and get some rocks from the fault zone and figure out what are their properties. And the questions were really fundamental. What's the strength of a plate boundary fault? Is it really strong with high friction, or is it weak? And what causes that weakness? Because we were worried that it was weak. So the idea was to drill down. You see this is the depth in meters, 3,000 meters. So they use kind of standard industry drilling technology to drill straight down and deviate the borehole across the fault zone, and then take cores across these different pieces of the fault zone or different interfaces that were slipping. This part of the fault kind of creeps, but it has some small earthquakes. And then get across to confidently sort of penetrate the fault zone. And you could see these high-resolution located earthquakes that sort of were right on, they're small, but on those slipping patches. And so it's possible to bring the rocks up. And this is a map view of the way that the coring worked. So the main hole and these side drills. And then this is the cross section. So we went down the red, and then these side shots to pull the cores out. So not huge cores, but something there. And so we could see these rocks are heavily deformed, pretty heterogeneous, and have zones of highly localized shearing and gouge formation. So it was possible to do some experimental work on these, and as you go across sort of along the core, they could measure the friction in the laboratory and show that indeed as you get into the main fault zones, the friction was low. So you could explain the fault strength as being weak because of material properties and not because of high pore pressure. And so the result from SAFOD, see if I can get the, that's next, is that it was profoundly weak. The weakness is due to the properties of the fault gouge, not fluid pressure. So it's these nanocoatings of talc on these sort of micro fault surfaces that keep it weak. The fault zone's narrow, it's highly localized, but there's more than one interface that's failing at any one time, and it was quite successful in answering this question about why the San Andreas is weak. So now, so that's that's the end of the cheese service, and now I will move on to a couple of sort of things you might think of for your next meal. So if you remember, yesterday I showed a similar enterprise. What was the last enterprise? Any Star Trek people? Well, the Enterprise was the first generation Enterprise. So this one is which one? I guess it shows my age, right? This is the next generation. So what's next? So, EarthScope, there's some planning activities, always planning activity for large-scale science activities. So what can be next? What should we be thinking about in 2020? This is totally relevant for the younger crowd who doesn't know that much about Star Trek, apparently. Is build on the scientific, technical, and broader impact success of EarthScope, have new partnerships. So one of the things I said was that the structural model of North America that we get from this really impressive seismological experiment still is kind of coarse. Like as geologists, like I'm thinking 70 kilometers, 50 kilometers individual values of seismic velocity. It's not quite at the mountain range scale, or it's kind of hard to think of every little fault in this whole system. So one thing that probably would be a good idea to do is to come together and kind of build a community geologic model that's four-dimensional, so we could really characterize the structures and material properties and history of North America at the geologically interesting scale, which is probably more at the kilometer scale. So this would be really exciting. It was huge value for applications like resource and hazards, but it would also let us kind of push to understand how the crust evolves especially. And we would definitely need lots of geochronology for that. So another opportunity that people have been talking about is to maybe provide more detail spatially, but also to take on an entire plate boundary. So another thing to do would be to do something called the Subduction Zone Observatory, and that would be to go basically from the Aleutians to Tierra del Fuego with heavy instrumentation, heavy integrated observations, geophysical, geological, to really understand the kind of all the variability of the sort of plate boundary processes and the associated hazards, and also even sort of hydrosphere and atmosphere interactions. So a lot of the observatories that we've built are really great platforms for sensing. So you can sense the motions with seismometers or GPS receivers, but you can also sense the atmosphere like water vapor with the GPS receivers. There's infrasound, so we could hear the Chelyabinsk meteor coming in across the US array infrasound microphones. So there's a lot of sort of kind of thinking this as this big sensing platform. And of course we would want to do a lot of geology. And so the one reason why this might be plausible just from a practical sense is there are a lot of networks that could be kind of stitched together. And that would be the basis of something like this Subduction Zone Observatory. We have what we have left from EarthScope, so Plate Boundary Observatory and various parts of U.S. array in Alaska and the lower 48. But then there's something called CocoNet and TlaLoCnet, which are parts of the Mexican subduction system. And then Chile especially has a pretty big investment in geophysical sensing kind of permanent networks. And so with that, you could string it all together and then have a bigger sort of science program on top of it. So that's just something people have been talking about. There's no sense that it will happen, but and I find it quite interesting to think big about these kinds of topics. So that's the end of my presentation. Any questions or additions?